excuse me. There we go. Now, what I'm going to do is I want to show you what we've been doing, and I'm going to try to get it so that it becomes kind of like second nature to you. So let's take a look at this page here. I told you that all of chapter 7 is right here, except for the horse cart problem. We're going to do that in just a minute. Let's take a look at Newton's third law. It's funny how almost everybody you talk to has heard this somewhere. Just like Newton's first law, they've heard of an object at rest. They can finish your sentence. They can say, has a tendency to stay at rest, right? And then you say an object in motion. They can probably finish and say, has a tendency to stay in motion, but they don't remember, has a tendency to stay in motion in a straight line at a, help me out, straight line at a constant speed. They don't remember that. And same thing here. Almost everybody has heard something like this. For every action, there's an equal but opposite. Okay, they say it, they can say it, but they don't quite get it. I want you to think about this. If Newton said, I can describe the motion of everything I know of in the universe in 3,000 laws. Well, maybe it would take 3,000 laws. No, it wouldn't 3,000 laws. Well, okay, 300 laws. Yeah, that'll do it. Everything in the universe, yeah. 300? No. 30? Oh, yeah, but you have to have at least 30. No. What do you say? 3. See, if you can describe the motion of everything in the universe with only 3 laws, this has to be important. It has to be much more important than these just people say it. So, what does he actually mean? And unfortunately, because we're human, we read it and say, oh, I know what that means. Something happens, and then later, something reacts to it. And he would have never said that. He would have never said it. He would say that the action and reaction occur at the exact same time. He would have said, you can't create a force. You can create a pair of forces, you can't create a force. You can't hit the table. You can't hit the table. But you can let your hand and the table hit each other. We don't have to think like that, do we? What do you think? So we have to make ourselves think a little bit differently if you're going to talk about Newton's third law. Objects don't act on objects, they interact with each other. You can't create, I can't touch the table unless the table touches me at the exact same instant. Now what do you know about the magnitudes? What about the magnitudes of these two forces? Right? Which one's greater? The force of the hand on the table or the table on the hand? They have to be equal. They have to be. Which one's greater? The force of the windshield on the bug or the bug on the windshield? They have to be. Which one's greater? The force of the earth pulling me down or the force of me pulling the earth up? They have to be equal. So if you look down there, on way down there, number 4, that's the hardest one that I find when people take tests. That's the hardest one for them. Ryan, can you do that some other time, please? That's the hardest one because the forces have the same magnitude, you're thinking, well, they'll have the same effect. But look down there at the drawing. Which one's greater? The force of the hammer on the nail or the nail on the hammer? And by now you said, they have to be the same. But what effect does that force have on the motion of that nail? Think about that nail, it's just sitting there. And all of a sudden the hammer hits it, and I'll ask that on the test I'll say identify A1. Identify A1. Here we go. Hammer pushes nail down. Now notice that force is not drawn on the hammer, it's drawn on the nail, right? Alright, so the hammer pushes nail down. A2. Nail pushes hammer up. Alright, I think I can do that. I can identify forces. Then I'll ask you another question. What effect does that force have on the motion of the object? So take a look at the nail. It's sitting still doing nothing. The hammer hits it, a force is on the nail. What's the effect of that force on the motion of the nail? All right, Sophia, you can do it. Yes, exactly right. Exactly right. All right, Michaela, you do the next one. What effect did A2 have on the motion of the hammer? Right, because the hammers are moving. So the effects look like they're different, aren't they? One of them is to accelerate something, and the other one is to decelerate something. So that's one reason why the effect might be different. One might be sitting still, one might be moving, right? And what's the other reason? Becky, you know that. What's the other reason why the effects would not be different? Well, let me ask this question. Which one of those objects is being accelerated the greater amount? Or are they accelerating the same? He said, like physics class, whenever he says or, excuse me. Or maybe he's trying to. Say it again? Why? Yes, that's really good. So another reason why the effects will be different is F equals ma, right? They both have the same forces acting on them. The nail's mass is tiny, isn't it? So the acceleration on the nail is going to be huge. But what about the deceleration on the hammer? It's there, but it's not huge, is it? Why? Because the hammer has a really big mass. That's great. If you can put all that together, you understand a lot. You already understand a lot. All right, let's look at number 2. Some people have trouble with this. Watch, person pushes table down, table pushes finger up, and question is, how come my finger is not going up? How come the table is not going down? And I know what you want to do. You want to say, well, they must cancel each other out. They can't. If they're part of the same action-reaction pair, they can never cancel each other out. Why? What? Finger pushes table. Finger pushes table down. That one? Table pushes what? Finger up. They're not both pushing on the table, are they? So they never act on the same object. They can't cancel each other out. Now, why isn't my finger going up? Why isn't the table going down? Let's think about this. As soon as I push the table down, guess what the 4 does? Pushes up. And then that force can be canceled by this other force down here, can't it? That could explain that. So you have to look for another explanation. You can't say if you're part of the same action-reaction pair, they can never cancel each other out because they never act on the same object. Here you go. Okay. Let's see, the next one, that's another thing I didn't understand. I really didn't understand this, and it was taught to me wrong a long time ago. I didn't understand that they had to follow a recipe. And remember how I talked about rockets? And how people told me, you know those exhaust gases that come out of the rocket? Well, when the exhaust gases come out, they push against the launch pad that way. That makes the rocket go the other way. There's a problem with that. Let's do the recipe. Exhaust gases push launch pad down. Launch pad pushes exhaust gases up. The missing word? Rocket. It doesn't say anything about moving the rocket, does it? Matter of fact, let me ask you this. Exhaust gases pushes launch pad down. What effect does that have on the launch pad? What would it do? Accelerate the launch, just like a nail. Accelerate the launch pad down. Launch pad pushes exhaust gases up. What effect would it have on that?
Pushes the gases up.
Which would decelerate them, wouldn't it? Wouldn't that decelerate them? And again, even though that happens, that has nothing to do with the rocket. And even if it goes away from the launch pad, exhaust gases push on air. Air pushes on exhaust gases. Again, nothing about rockets here. So let's take a look at that one more time. Let's do rockets one more time. It really does, whether it does for you or not, it means a great deal for me, for you to understand how this works, because for so long, I had the wrong idea, and I want you to have the right idea. So let's take a look at this, and I'll do this again. This is like a rocket in a way. And if you can pretend it has a knot in it, just pretend, okay? So if it has a knot in it, then watch the arrows, ready? Identify this arrow air pushes the balloon that way. Balloon pushes air that way. Is you okay on that one? Let's go to the other side of the balloon. Air pushes balloon that way, and balloon pushes air that way. Now, these two can never cancel each other out, but can this one be canceled by that one?
Yes.
Yes. And so what happens to a balloon that has a knot in it? What is the net force on the balloon? If every one of them gets canceled out, what's the net force on the balloon? And that's why it doesn't accelerate. What is the net force on the air in the balloon? Zero. That's why the air doesn't accelerate. Now, what happens here, and if I hold this balloon too long, it won't work. I'll do it again. But what happens when I create a hole? And that's what I want you to think about, all right? As soon as I create a hole, then, remember, balloon pushes air that way, but there used to be another one, balloon pushes air that way. It's gone. It's gone because there's no balloon there. So what is the net force on the air in the balloon? Down, toward the hole, okay? And so as soon as I let go of that balloon, there's a net force that says accelerate the air toward that hole. At the same time, you start pushing the air toward the hole, then what happens to the balloon? What's the net force of the balloon? This used to be canceled out by this one. There is no force there. So what's the net force on the balloon then? Away from the hole. You get it? It's just like the rocket. The rocket, I don't really care about the air that's already left the balloon. I get it. The air that's already left the balloon, what's it going to do? Ready? Sorry. Air that's left the balloon pushes the air in the room that way. Air in the room pushes the air that's left the balloon that way. See that? But then tell me why the balloon moves. So then, where is the action-reaction pair? It's in the balloon, isn't it? It's not when the air comes out. It's when it's being pushed toward the hole. Now, let's make a balloon that's much sturdier. Let's make a balloon that's called a combustion chamber. Let's make it really strong. And put some gases in there. Does anybody happen to know what the most common chemical reaction is in some rocket engines? Are you guys so young? Do you remember the space shuttle? Did you ever see the space shuttle? Okay, so does anybody know? Here's the space shuttle. You got the orbiter. That's not very good. Okay. You have the orbiter right here, and that's where the astronauts are inside here. And then you have this, whoa, big tank here. Yeah. Do you remember something like that? You ever seen the space shuttle? Okay. All right, ready? The orbiter is the, everybody says that's the shuttle. It's called the STS, Shuttle Transport System, STS. Anyway, this is where the astronauts are in here, get it? Now, what happens is, this right here has something huge in it, and these right here are called solid rocket boosters. Now, what they have is, they have solid fuel. They have solid fuel in them, and when they're like fireworks. They're like, ever done bottle rockets?
Yes.
You light them, they go off like that? That's what this is. Ever done model rockets? Model rockets got a little, they call it an engine, and you put electricity to it, and see that? Okay, good and bad. Those are cheap to make, and but guess what? They have a drawback. Once you ignite them, you cannot stop them. If the astronauts, if they said 3, 2, 1, and they press that launch button, as soon as those start, you cannot stop them. You are going to go for a ride. You get it? Now, after they accelerate the astronauts, and they start getting up, and up, they burn out, and then they drop them off. They fall into the ocean, and they go pick them up and reuse them again. Okay? Elon Musk, he somehow, I don't know why NASA couldn't do this. Guess what he did? He made these rockets do what? They can actually return and land themselves on a platform. Why couldn't NASA have thought about that? Anyway, so now they're gone, and now you have all this. Now, does anybody happen to know what the fuel is there?
Liquid.
Yes. One of them's called LOX. What's that?
Liquid oxygen.
Liquid oxygen. And if you liquefy it and cool it, you can have more in there, right? And then the other one is this guy right here, hydrogen. And so if you can burn hydrogen with oxygen, you can create a great deal of force with that. All right, so I want to show that to you because that's what that picture is. That's the STS, the Shuttle Transport System right there. All right. So the combustion chamber is like the balloon, but we want to make it strong because we want to be able to, when the gases expand, gases push the chamber walls that way and that way and that way and that way. What are the combustion chamber walls going to do? Push the gases that way, that way, that way. Now, if you don't have an opening here and you let that reaction take place, what's that called? It starts with a B. If you close this up and let the reaction take place, what do you have?
A bomb.
A bomb. We don't want a bomb, so they have an opening. And so what happens with the opening? As soon as that thing starts doing it, everything will get canceled except for the net force on the gases in the combustion chamber will be accelerate them toward the hole. And what's the combustion chamber going to do? Accelerate away from the hole. Notice I don't care about the exhaust gas. Get it? The exhaust gases mean nothing. So the exhaust gases, yeah. Exhaust gases push launch pad down. Launch pad pushes exhaust gas up. Good. There's no rocket in there, is there? I don't need to push against, my exhaust gases don't need to push against anything. Here's where the action-reaction takes place. See it? And that was not something I was taught. And it made me feel funny that one time, it was 45 years ago, yes, but it made me feel strange to say when somebody said, well, do rockets work in space? And I was taught that it was the exhaust gases that had to push against something. That's why I had trouble answering it. So eventually I figured this out, and that's how rockets work. Now let's go to the next page here. This has to do with the, kind of like the horse cart system a little bit. So I'm going to start talking about that today. Let's see. I don't know. Ryan, can you see this drawing?
Yeah.
Okay. Are you all right? This says F1. This says F2. Can you identify F1? Identify F1.
Tell you where it is.
Yeah.
Oh, that's right. On the right.
So in this chapter, when I have done these thing called force diagrams, and I ask you to identify them, it always fits the recipe. Object A pushes or pulls object A. A acts on B, B acts on A. So what do you want to put here?
Oh.
I'll give you a clue. Can I give you a clue? Since the tail of the vector is drawn on a football, don't say the word football first.
Yeah, the foot pushes.
Which way? To the right. Ready? You're correct. Ready? Foot pushes football to the right. Go ahead, Ryan. Do it again. F2.
The ball pushes the foot to the left.
Yes. That was easy, wasn't it? All right. Everybody got that? All right, Maggie, down here. Maggie, I'll do the first one for you. F1 is dark foot pushes ball to the right. F2, football pushes dark foot to the left. Now I want you to do L1 and L2. What's L1? What's L1? I'll give you a clue. The tail is drawn on the football, so don't say the word football first. Which foot? Light foot pushes football to the left. Now this one. Everybody get it? That's pretty simple. And I've actually seen this, especially with little kids in soccer. When will this ball not accelerate?
When they kick the same force.
All right, and then use letters for me. Help me with some letters. I see 4 forces. Tell me which force I'm looking at. Go ahead. That ball will not accelerate if blank equals blank.
How about if
It's hard to read.
Yeah,
F1.
F1 equals L1, right?
Yes. Now, what if F1 is greater than L1
Sorry.
to the right? Everybody get that? So I've seen two kids playing soccer and they hit it exactly the same like you said, and the ball stays right there. And I've seen that. I've also seen it where it doesn't stay right there. All right. Now, what I'm going to do here is we're going to get into the horse cart problem. All right. And so what I'm going to do is, this is the last part of the chapter, and it's kind of neat. It's kind of neat. And so I'm going to go over here, this drawing here. All right. Now, I don't know why the author wanted to put an orange in a cart. I guess he just wanted you to think about something else. But we have this saying, if you ever become an engineer, you'll have discussions with other engineers, and you might talk about things called systems. Now, a system is whatever you define it to be. If I define the system to be just the orange and another system to be the cart, then I have two different systems, right? And that means they could interact with each other. But what if I define, see this dotted line? The author says, let me define the system as being everything in that dotted line. Now the orange and the cart are not two objects. I hereby define them as being one object. Can I have any forces that could cause a change in my motion then? How many objects are there? Help me out. There's only one. How can one object create a pair of forces with another object? It can't. And so I'll tell you what that means. For example, right here. I'm on a chair here, okay? I and the chair are one system now. Ready? All I'm going to do is I'm going to go to that door. Here we go. Ready? Now I am pushing on that chair. I am pushing on that chair. That way. I should be going that way. But I can't, because the chair and me are now one object. So any pushes that take place within the same object, it can't cause any change in my motion. So now, what if I want this system to accelerate? Yes?
What happens when you go like this? Well, not that. Like if you lean back and forth. Like.
You can have what they call a change in momentum. You could try to do that. But if that chair was not attached to the floor, if you were in space, what would happen? You could wiggle all you wanted, but you wouldn't go anywhere, would you? So what you're thinking I'm not interacting with the floor, but you are when you do that. So let's look at this right here. If that's one system, and by the way, if you were to fall off a cliff and you always say to yourself, why don't I just reach behind myself and push myself back up the cliff? You can't. Why don't I get on a sailboat? Why don't I get on a sailboat and have a battery-powered fan, and simply turn the fan on, and I can go sailing when there's no wind? No, you won't. And so what we need is, if this is one object, I need to interact with another object. So now, let's put the apple here. Ready? Apple pulls orange cart to the right. Orange cart pulls apple to the left. That's nice. If we were in space, though, and the only two objects are these two objects, what would happen if I pull you and you pull me? I could pull you toward me. You could pull me towards you, couldn't you? But then, what if I thought of you now as one system? What if the apple-orange cart is not two objects anymore? There's one. And this is where the horse cart problem comes in. It's possible that this guy could still pull on you and you could pull on it, right? But if this is one object and not two, can this cause, these are called internal forces now, they cannot cause a change in your motion. So now we need another character to come into play. What's the next character that has to come into play? Right. What you got? I need you to move up here, okay, or else put all your stuff up. We need another player here. If this all one thing is called a system now, that's one object, I can't go to town. The horse cart can't go to town. And the horse was correct when he said, for me to pull back on the cart, it's futile, because the cart will pull me backwards, and we won't go anywhere. He was correct when he said that. But eventually the farmer says what to him? What did the farmer say eventually to him? Yes?
The ground will accelerate.
He needs another object, doesn't he? If the horse cart is one object, I need it to interact with something else, and that's called the ground. So watch what happens here. Ready? The horse cart pushes ground backwards. Ground pushes horse cart what? Forward. You get it? And that's how they are going to go to town. Now, I want to show you, what I'm going to do right now is I'm going to explain the horse cart problem to you. And I'm going to go ahead and make this picture a little bigger. And that's what your assignment is. Okay, now, your assignment, I'll explain that assignment in just a minute here, but you're going to make a force diagram with a horse cart problem situation. And I hope you enjoy doing that. I showed you some the other day. You can see how they enjoyed doing that. Everybody had their own little thing they want to play. So anyway, I'll tell you one thing I didn't like about the author. He does a great job in this book, but I think a mistake he made here, and that's my opinion, he did not put letters like I did. He did not put numbers. He didn't put subscripts. And I think if you're just to read this by yourself, you would get confused. So what I'm going to do is I'm going to put little subscripts on these letters, and I'm going to go around the room and ask people to identify them. And if we can identify them, we're halfway there. Okay. Let's see. We'll start. Maggie, you start. We'll go right down the row. And what I want to do is, do you see the 6 arrows that are drawn here? Can you see them? Okay. All right. I want you to identify capital F1. I'm going to give you a little help here because since the tail of the vector is drawn on the horse, don't say the word horse first. All right, here we go. Identify capital F1.
Which one's that one?
Say it again.
Which one's that one?
This one.
The brown pushes on the horse,
Which way?
right?
Yes. Everybody see that? Ground pushes horse to the right. All right, Clay. How about big F2?
The horse pushing the ground left.
We got it. All right, McKinley. P1. P1.
Where's that?
P1.
Oh, cart pushes horse left.
Or pulls, okay. Pulls horse left. Yes. Okay, Becca. P2. Yes. And here's the hardest one. All right, so 5. Little F1. This is the hardest one. Little F1.
The ground.
Now wait, if it's drawn on the ground, don't
Sorry.
say ground.
Pushes.
Start again.
You said little F1.
Yeah, huh? I'll give you a clue. There are 3 objects: horse, cart, ground. So what 2 objects do you think are interacting there?
The ground and the cart.
Okay, yes, keep going. You can't say ground first, so you're going to say what?
The cart
Say it.
pushes the ground.
Which way?
Right.
That's right. Now, you know why you don't like this? I'll tell you why you don't like that arrow there, because you don't believe it. You think that the cart is going to push the ground backwards. That's not what's happening here. If I had a motorized wheel, the wheel would push the ground backwards, and the ground would push you forward. This is not a motorized wheel. If you're ever going to the beach and you had to have a cart, anybody have a cart or something, or a cooler that had wheels on it? You're trying to pull it along the beach. That's what that happens. What happens when the wheels hit the sand? What does it do? Not a motorized wheel. What's it do to the sand? It pushes the sand that way, doesn't it? This wheel has a tendency to push the ground to the right. And what does the ground do? Push the cart to the left. Everybody see that? All right. Now, you with me?
Is that correct?
Yes. Very good. Now, let's think about this now. This is the good stuff right here. Tell me, will the horse accelerate to the right?
Yeah.
And I'll give you a clue. Who do you leave off with? All right, Clayton. I'm going to give you a little help, Clayton. Is the horse going to accelerate to the right? And I'll give you a clue. These are on the ground, don't look at them. These are on the cart, don't look at them. Is the horse going to accelerate to the right?
Yes.
Why?
Because the
Give me some letters.
P1 will be one for F1, capital F1 is greater than.
Yes, yes, yes. If big F1 is greater than P1, there'll be a net force to the right, and the horse will accelerate to the right. Okay, Ryan, your turn. Ryan, tell me about the ground. What will happen to the ground?
Well, because big F2 is greater than little F1.
What's going to happen then?
The ground's going to get left.
Go left or?
Accelerate.
There you go. Accelerate to the left. All right. Avery, your turn. Tell me about the cart. We don't need to look at anybody else. Will the cart accelerate to the right? Yes or no? Sometimes it does, and sometimes it does, but the cart will accelerate to the right if blank is greater than blank. Help me out. Okay, if little f2 is greater than p2, what's going to happen to the cart? If that there is bigger than that, the net force will be backwards, won't it? But what if I want the cart to go to the right? Then who has to be bigger? P2 has to be greater than little f2. And now, the final question. Owen, perfect ending. Will the horse cart go to town? Will the horse cart accelerate to the right? You'll say yes if, finish the question for me. Now the horse cart is one object, not two. Will the horse cart accelerate to the right?
Yeah.
Yes, if what?
I don't know what you're trying to say.
Okay, and I'll show you what I'm going to look at, right? If the horse cart is one object, we don't need to look at the ground because that's not affecting that object. And these can't exist. They're internal forces because I'm not two objects anymore, I'm one. So now you only have two forces left. The horse cart will accelerate to the right if...
Oh, it's greater than, the force is greater than. the
Tell me
net
some
force is
letters.
greater than
Give me some letters.
If if F2 is, or not, I can't read what that letter is.
What? You can't see it?
No.
Okay. All right, can you see this one? That's big F1.
Oh, well, if F1 is greater.
Big F1?
Hmm?
Big F? Capital F?
If F1 is greater than, the friction,
Which is what? There are two frictional forces.
F2.
Yeah. Okay, so if big F1 is greater than little f2, then the horse and cart will go to town, won't it? So if they happen to be in some mud, it's very possible that this force could equal this force. And the horse is pulling, and they don't go anywhere. And whoosh, whoosh, they get the whip out. And what does the horse do? The horse pushes harder on the ground. What does that do? that makes this greater than that. And that's how they get out of the mud. All right, so let's take a look at, Sophia, can you hand me one of those, please? And I only have a few minutes to help you out a little bit here. Thank you. Thank you very much. All right. Now, this project takes a lot less effort, and it's more creative in a way. I like your experiment, but I have another project for you, and here's what we do. Let me demagnify for a minute. All right, here we go. Horse cart problem. Number one, you are to draw a horse cart situation like the one in the handout, and it cannot be a horse and a cart. So you have to think of something besides a horse and a cart, but it has to have the same 6 forces that you had on the horse cart problem. You get that? Now, you will get 15 points for number one. Number one says, draw a horse cart problem, but not really a horse cart, and be creative and colorful. 15 points. Think about it. I could do that. 2, draw the 6 forces involved. Remember to use the same letter but a different subscript for the action-reaction pair. For example, you might have A1 and A2. You might have B1 and B2. And it says here, the tail of each vector must be on the object that it acts upon. Everybody okay on that? Now, here's where people lose points every year on this. They think they can just draw an arrow any size they want and call it F1. And then they put another arrow, which is a different size, and call it F2. You can't do that. How can an action-reaction pair have different magnitudes? They can't, can they? And if it says the tail has to be drawn on the object that it acts on, then make sure the tail's on that object. Let's do number 3 now. Identify each drawn vector. So I look at your A1 vector, and I see where it's drawn, and I go up here and I say, did they identify A1? A1, horse pushes ground to the left or backwards. A2, ground pushes horse forward. See that? That's pretty easy. That's pretty easy there. And so you get points for identifying those. Yes?
Is there a way that friction is greater than the force acting?
Say it one more time.
So I realize that friction can be equal to a force acting opposite it. Can it be greater than a force acting opposite it? So is there any world where
It-
F2
you know,
is greater than F1?
I think it could be greater. Well, I don't know of any situation where it could be greater. I'm trying to think of one. Right now, I can't think of one. Either I push the cart. I don't see how if I push a cart, it's going to make me go backwards. I don't see pulling a cart, how it's going to make me go backwards. I don't know if you can think of some situation. I'll give you some credit for that. Right now, I can't think of a situation where that would happen. And the last thing here, and this is for 5 points, is think of the horse cart now as one object. Answer the following statements using the symbols F1 or P1 or whatever you want to use, and use one of these symbols and tell me the horse cart system will accelerate forward when blank, blank, blank. If you want to say equals, greater than, less than, you can do that. So I want you to think about that. And, okay. I think that's it. What do you think? I want you to have fun with this. Think about it today, and you don't have to finish it tonight. Maybe you just want to think about the idea, how to do it. And then, so you get some points for being creative, but then you get the points for the physics of the project also. Now, right now, we have a little bit more to talk about rockets and orbits, and that'll be on Monday and Tuesday. I'm going to look on the calendar. I still think I'd like to wait till Thursday to have our test. So I think I might do that. I'm going to look on the calendar again, but I think you could do really, really well on this, I believe. All right. Anybody have any questions? All right, there we go.